In this session, we're going to explore sigma, or summation notation, which is so named because the Greek letter sigma is used to indicate a sum. This is an example of looks difficult until you know what the things mean. An example of what you might see with a sigma notation would be sigma with I equals 3 at the bottom, and then 2i plus 5 next to it, with maybe a 15 at the top. And it's a bunch of symbols that doesn't seem to make much sense. But I want to relate it to what you know about functions. If we have f of x is equal to 2x plus 5, you know that x is the input variable. And using an xy table, if I put values of x into the function, say 3, 4, 5, etc., then on the right-hand side, the 2x plus 5 gives me a rule to follow. And knowing what the rule is, we can say that the answers are like 11, 13, 15, just by putting different values in place of x. The letter at the bottom of sigma notation is referred to as the index, and it acts like the argument in a function. It tells you what variable you have that's changing. The number I equals 3 gives you your starting value, and so that's akin to doing an XY table starting with 3. And the terms of the sum are going to be like a sequence, except they're added together, so it's really just a series. And the 15 at the top just tells you that the last number I'm going to put in is 15. The index isn't always I. You might see the sum as j goes from 1 to 12 of 2j plus 17, or something like that. What matters is not whether it's an I or a j. What matters is that the letter underneath the sigma is the same as the one in the parentheses, or in the argument. It's not always parentheses, but in the argument of the sigma notation. And in the case of what I just wrote, the j going from 1 to 12 means that we're going to have 12 terms where j is going to be 1, j is going to be 2, etc., all the way up to j being 12. And the argument, if you will, of the sigma notation tells me how to figure out what the terms are. Finally, once I know how to figure out the terms, this is summation notation. Sometimes called sigma, sometimes called summation, but keep in mind this means that we're adding terms together. And this is just what we're going to see in our first example. We're asked to write out the sum, and here we have sigma notation. The sigma with the I equals 3 underneath and a 9 above, with the I minus 1 quantity squared, is red. The sum, as I goes from 3 to 9, of I minus 1, the quantity squared. That's how we say that out loud. I starts with 3, and then I is going to take on integer values all the way up to 9. So that becomes our input each time. And so for our first term, we've got 3 minus 1, the quantity squared. For the second term, we've got 4 minus 1, the quantity squared, and so on. And if this feels like writing out the terms of a sequence, it is a lot like that, but there's the one difference. This is a sum. That's what the sigma notation means. And so between each of these terms, 3 minus 1, the quantity squared, 4 minus 1, the quantity squared, we should put a plus sign. And this is how we can indicate that sigma notation is adding all this stuff together. Doing some quick simplifying, we can rewrite this as well, that's writing out the sum. To actually find the sum, I'm going to put all this into my calculator. Alright, I lied. I just did it on paper. The answer I come up with when I add all this stuff up together is 203. So write out the sum, a bunch of squares added together, find the sum, do just that. For our next example, write out the sum. The sum as j goes from 0 to 4 of the fraction 2j minus 1 divided by 3j plus 1. And then after that, we're to find the sum. Well, to write out the sum, we need to figure out what the terms are, when j equals 0, when j is 1, 2, 3, and 4. That's not necessary to write down j equals 0, j equals... I'm just doing that to show you what's going on. When j is 0, we're looking at 2 times 0 minus 1 divided by 3 times 0 plus 1. When j is 1, we're looking at 2 times 1 minus 1 divided by 3 times 1 plus 1, and so on, putting 2, 3, and 4 in place of j in each of the terms as appropriate. That's not the sum, though. Those are the terms. The sum is the sum. And so we put plus signs in between these terms and simplify each term. For the first term, 2 times 0 minus 1 is negative 1, and then 3 times 0 plus 1 is 1. And then we just simplify down the line. So we have plus 1/4, plus 3/7, plus 5/10, plus 7/13. And then to write out the sum, I should tidy this up just a little bit. So we have negative 1 plus 1/4 plus 3/7, 5/10 reduces to plus 1/2, and then plus 7/13. That is the sum written out. To find the sum, we need common denominators. I'm actually going to push some buttons here. And the sum that I get is 261 divided by 364. If you needed a decimal approximation, probably 4 decimal places is good. We've got 0.7170. So there we are. Next, we're asked to write out the sum as k goes from 1 to n of negative 1 to the k minus 1 times the natural log of k. What am I supposed to do if it doesn't have a number at the top, but it has the letter n? Well, you go up to n. The way we're going to do that is, first we're going to consider, k equals 1, k equals 2, k equals 3. But then we're going to go generic, and I'll show you what I mean. First, if k equals 1, we have negative 1 to the 1 minus 1 times the natural log of 1. If k equals 2, then we have negative 1 to the 2 minus 1 times the natural log of 2. And then, of course, you know what we're looking at for k equals 3. Negative 1 to, make sure we can see what's going on here. I'm going to highlight our terms and then note that they should be separated by plus signs. After that natural log of 3 term, I'm going to put a dot, 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 and I'm going to put plus. This is supposed to go up to n, and the way I can indicate that is to say it's negative 1 to the n minus 1 times the natural log of n. And you might say, wait a minute, all you did was you replaced that k with n. Yeah, that's what we're doing the whole time here. These negative 1 to the powers, remember these are going to give us alternating signs for our terms. So for the first one, negative 1 to the 1 minus 1, that's negative 1 to the 0. That answers 1 times the natural log of 1. Plus, now negative 1 to the 2 minus 1, that's negative 1 to the first power. It's not a plus, is it? It's a minus natural log of 2. For our next term, it's going to be plus the natural log of 3, and you can see how this would play out. And as soon as you can see how this would play out, we can put plus dot, dot, dot. Now, I'm not sure if n is going to give us a positive or negative for the base of negative 1, so I don't bother. I'm just going to write down what that nth term would be generically, which is going to be negative 1 to the n minus 1 times the natural log of n. You might be looking at this saying, hey, we can simplify that first term. And as a matter of fact, we can. Turns out natural log of 1 is equal to 0, isn't it? So if we were to simplify this, we would say this is negative natural log of 2 plus the natural log of 3 minus the natural log of 4. Hey, where'd he come from? We knew what was next, didn't we? Plus dot, 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 plus negative 1 to the n minus 1 times the natural log of n, and we have now written out this sum as we were directed. Now if that n up there weirded you out this time, then check this out. We have the sum as I goes from 1 to infinity of 2i minus 1. That's not fair. Sure it is. It just says that this series never stops. All we're asked to do is write out the sum, and so when I is 1, we're looking at 2 times 1 minus 1. When I is 2, we've got 2 times 2 minus 1. When I is 3, we've got 2 times 3 minus 1. And each of these terms should be separated by plus. And then after that last one, we can put dot, dot, dot. That there's nothing that comes after the dot, dot, dot indicates that this is an infinite series. We can simplify each answer though. 2 times 1 minus 1, last I checked, is 1. 2 times 2 minus 1, last I checked, is 3. 2 times 3 minus 1 is 5. And then we can put plus dot, dot, dot. And now we've written out the infinite series. We've written out the sum that goes to infinity by indicating it just doesn't stop using the dot, dot, dot. Now we're given a series and we're asked to write it using sigma notation. And what we have is 1 minus 2 plus 3 minus 4 plus 5 minus 6. What we need to recognize is that the first term is, which is 1, is when I equals 1, or J or K. I don't care which letter you use. The second term is when I equals 2. The third term is when I equals 3. So this is kind of like finding the nth term of a sequence, except we need the nth term of the series to put into the sigma notation. If when I equals 1, I have 1, and when I equals 2, I have negative 2, and that pattern continues, and I can see we have alternating signs. So somewhere in here, I need a negative 1 to show up. When I equals 3, my term is 3, but when I equals 4, my term is negative 4, so I have this negative 1 popping up again, times 4. What I need is, on the terms that are positive, that negative 1 needs to have an even exponent. When the term is negative, I need that negative 1 to have an odd exponent, and so on. Recognizing this, I can write, sigma, sum, I equals 1 underneath. You can see that we have 6 terms, and so if I starts at 1, it's going to end at 6. I, as an argument, is what's going to give us 1, 2, 3, 4, 5, and 6, but we need to have a negative 1 running around, right? So, I don't like where that is exactly. We're going to have a negative 1 running around, and we could experiment by putting negative 1 to the I times I. But if this were the case, then when I equals 1, I'd have negative 1 to the first power times 1, which would give me a negative 1. But we already decided that the exponent for the odd terms should be even, and so we can use plus 1 to get out of that. Now we would have, when I equals 1, negative 1 to the 1 plus 1, which would be a positive term. We can verify that it works the way it's supposed to with subsequent terms. But here we have it. The sum as I goes from 1 to 6 of negative 1 to the I plus 1 times I. Next we're asked to write out a series using summation notation, and the series is 1 plus 8 plus 27 plus dot 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 plus 8 cubed. Wait a minute, this says summation notation, and the last one it said sigma notation. Yeah, they can be used interchangeably. What we need to know is we're going to be using the sum, and I need a starting value. I also need an index variable, and this time I'm going to use j, just for the heck of it. For the first term, 1, we could consider j as 1. For the second term, 8, we can consider j as 2, and then j as 3. And if that's the case, well, I need to know what the rule is. If j is 1, and that gives me 1, and j is 2, and that gives me 8. That doesn't tell me much, but when I put that together with j is 3 giving me 27, now I'm starting to think, hey, I think these are cubes. Like 1 is 1 cubed, and 8 is 2 cubed, and 27 is 3 cubed, and oh yeah, 8 cubed is 8 cubed. So this sum is going to be, as j goes from 1 to 8, j cubed, and that's it. But what if we wanted to be a little creative? Instead of j starting at 1, suppose I wanted j, well, I've already used j. Suppose I say, you know what, this is k, and it's going to start at 3. Well, we can do this if we really want to. We would just have to change the terms appropriately. So k equals 3, that would be the first term, so the number would be 1. K being 4, these have to go sequentially, is going to give me 8. K being 5 is going to give me 27. I still have cubes, right? These are still cubes. But I need to relate what I'm cubing with what k is. So we know 1 is 1 cubed. If k is 3, then I'm really looking at 3 minus 2 cubed, right? If k is 4, I'm looking at 4 minus 2 cubed. And if k is 5, this is 5 minus 2 cubed. So what I see is the same is the 2 in each case. And what I see is increasing is 3 minus 2 cubed, 4 minus 2 cubed, 5 minus 2 cubed. This gives me the idea that the argument of my summation notation is going to be k minus 2 cubed. And I can see that that works, but here's the deal. The upper limit of this sum isn't going to be 8. I still need to have a total of 8 terms. And considering our rule where we have something minus 2 cubed, if, scroll up, the last entry here is 8 cubed, then the thing I'm subtracting 2 from to get 8 must be 10. So the upper limit of this sum would be 10. We would end up with the sum as k goes from 3 to 10 of k minus 2, the quantity cubed, which is just a different, maybe more interesting way to write the original sum. Comparing the two, by the way, if j is 1 and k is 3 for our starting points, then we could say that k is equal to j plus 2, which means that j relates to k in such a way that j, subtracting 2 from both sides, is equal to k minus 2, and we can see that the arguments of the two representations that we have agree in that sense. Next, we're asked to write a series using sigma notation. Oh, summation, sigma. Get it straight. No, you have to deal with both of them. And the series here is 1 over 1 plus 2 plus 1 over 2 plus 3 plus 1 over 3 plus 4, and then we're back to this plus dot 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 1 over n times n plus 1. Well, this is a sum, so I'm going to use a sigma. I, j, or k. Well, we just used j and k, I think, so I'm going to go back to I. And it's easiest if we can deal with it to make I equal to 1. And since I see that last term has those n's, I'm thinking that the top limit is going to be n. So already we know it's the sum as I goes from 1 to n. Now how do I express these terms? Well, it was kind of gift wrapped for us when that last term was n times n plus 1, but even if it wasn't, the denominator of the first term, 1 times 1 plus 2, is 1, and then 1 plus 1. The denominator of the second term is 2, and then 2 plus 1. Quick inspection tells us this pattern continues, and so I'm thinking we can put the sum as I goes from 1 to n of 1 over I times I plus 1. Alright, 2 more examples and then we're done. Next we're asked to write the series using summation notation, and the series is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... That's one of these where when I write the sigma, the guy at the top is going to be infinity. This one doesn't stop. Now for our individual terms. We can use j. When j is 1, the answer is 1. When j is 2, the answer is 1/2. When j is 3, the answer is 1/4. And when j is 4, the answer is 1/8. Let me write all that in a slightly different way here. J is 1, I have 1. J is 2, I have 1/2. If that were all we had, I might think that this is like 1 over j, right? 1 over j. But the next one blows that idea out of the water, because when j is 3, my value is 1/4. So how can I... Well, maybe it's a good idea to write down j is 4. That term is 1/8. Noting a pattern in the denominators, looks to me like 1/2 is 1 over 2 to the first power. 1/4 is 1 over 2 squared, and 1/8 is 1 over 2 cubed. Verifying that the first term is 1 over 2 to the 0 power, I see there's a pattern that I could use. I could say that j starts at 1, and our terms are 1 over 2 to the j minus 1 would give me 0 for the first exponent in the denominator, and then when j is 2, it would give me 1 as an exponent in the denominator, and so that would work. What we just saw a few minutes ago with different indices indicates that instead of writing it that way, argument suppose I say j instead of the sum is I goes from 0 to infinity of 1 over 2 to the I. What we've done is we've changed our starting point, but we've also changed the argument. And in this case, we don't have to fix the upper limit because it's infinity. And if you add or subtract, say 1 from infinity, you haven't changed anything. So either of these two, the sum is j goes from 1 to infinity of 1 over 2 to the j minus 1, or the sum is I goes from 0 to infinity of 1 over 2 to the I. Either one of those would be fine with me. For our last example, we're given a series. The sum is I goes from 7 to 12 of 3i minus 4. And we're asked to rewrite it using a new index as indicated. And what we have is a blank sum, but it says j equals 1 at the bottom. What we need to do is figure out what a new argument would be and a new upper limit would be if instead of starting at 7, we started at 1. The trick here is to see how I and j relate to each other. And if I is 7 and j is 1, then it seems to me like I is equal to j plus 6. That seems to work. And you can see if j is 1, then I is clearly 7. There it is. And if that's the case, so the argument originally was 3i minus 4. Let me highlight that I. And I want to replace that with j, and since I is j plus 6, then where I see I, I'm going to write down j plus 6. So I have 3 times the quantity of j plus 6 minus 4. When I simplify this, I get 3j plus 18 minus 4, and so 3j plus 14 is the result. That becomes the new argument in my sigma notation. So I have the sum as j goes from 1. I'll figure out the top limit in just a minute, but the argument is 3j plus 14. For the top limit, originally it was 12, right? So now that was an I limit. Let's keep that in mind. I had I was equal to 12. What I need is what j is if I is 12. If I take this I equals j plus 6, and solve for j, then I have j is equal to I minus 6. And what this is a relationship that tells me what j is for any particular I value. If I is 12, as it was to begin with, then j is going to be 12 minus 6, which is 6. And so the sum, my new one, becomes the sum as j goes from 1 to 6 of 3j plus 14. If I wanted to double check that everything was correct, then I might look at the first term and see when I is 7, I have 21 minus 4, and that's 17. When j is 1, I have 3 times 1 plus 14, which is also 17. That's not a proof that everything works, but it's a pretty good indicator that I'm probably on the right track. If I really wanted to, I would just check more terms. But this is how you can change an index.